Okay, so y'all probably remember this from chemistry. You've seen the periodic table. We're going to look at a few things, and we're going to start off really with the basics. So this is super review from what you've had in chemistry. First of all, we have a nucleus. You guys remember what that is? Center of the atom that has the protons and neutrons. And then we have orbitals. And we're not going to go into chemistry and look at the different types of orbitals. We're just in general, we have this outside area, and that's where you're going to find those electrons. You remember from our electrostatics units, we have charges, positive charge on the proton, negative charge on the electron, about the same amount, a certain amount of coulombs per electron. And then when we're thinking about masses, protons and neutrons are about the same mass, and then electrons are going to be a lot smaller than those protons and neutrons. So this is not really to scale. That electron should have been a lot smaller if I was trying to be to scale. So the subatomic particles, which just means the things less than an atom, are going to be our protons with our positive charge, our neutrons that have no charge. And then within that, I just want to remind you, if you have two protons, are they going to want to stay together? The two protons, no, they're going to want to, because of electrostatic or electromagnetism, electrostatic force, they're going to want to separate. So there is a stronger force that we'll talk more about later that helps cement these particles together. It's called the strong nuclear force. There's a strong nuclear force in there that's holding these things together. I'll talk more about that in the next lesson. So the only reason why any sort of reaction would ever occur, and this goes back to chemistry, is first of all, because they want a bond to become more stable. It's all about stability, and you might want to highlight that. Anything that occurs in atoms always occurs to become more stable. And bonding is one example, and we're not going to go into bonding. We're not going to spend much time with that. We're going to spend more time tomorrow looking at the nuclear decay reactions. And that's what we'll focus our efforts on, which you should have had in chemistry. For the most part, it should be a review on that lesson too. So we have two things that can happen. Just so atoms, specific atoms, elements could become more stable. They may change. They may combine as a bond, or they may decay and become something else. So here's our periodic table, and there's a few things that we're going to focus on specifically. The atomic number is going to be probably the most important thing. And then the atomic mass may be important for some questions, depending on if I give you a little bit extra information. We'll look at that extra information right here. The atomic number is just number of protons. If you don't remember that, make sure you highlight that. When I see 7 here for nitrogen, I know nitrogen has 7 protons no matter what. And there's going to be these things called isotopes, which come in with different numbers of neutrons. But I know nitrogen, if it's nitrogen, it has to have 7 protons. That's the definition of nitrogen, comes in with 7 protons. And if I think beyond that, and when you look at the periodic table, so just going at what I'm talking about here, when you look at the periodic table, you're going to see, and there's a lot of different ways you can set this up. You're going to see a small number, you're going to see a bigger number, and often that bigger number is going to have like a decimal. But nitrogen, if it's nitrogen, you look at that smaller number, and that will always be the atomic number, and that will tell you how many protons that nitrogen is bringing in. And if it was neutral nitrogen, in nature, everything overall kind of is neutral. When there was a proton, there has to be an electron. Well, if it was neutral nitrogen, if it has 7 protons, it would have also had those 7 negative electrons. And then that gets us to isotopes. So this is really the majority of today's lesson, where it may be, it should be a reminder, but there's going to be a few little, maybe one fact that I might kind of catch you on the quiz, and then if you get caught on it, you'll learn more because of it. But isotopes, if it's nitrogen, every single one of these nitrogens has 7 protons. Every single one, nitrogen 13, nitrogen 14, nitrogen 15, all brings in 7 protons. And they're going to be all isotopes. And whenever we're trying to think about the most common isotopes, for the most part, now there are some exceptions. Whatever this number is closest to, everybody see how it's 14.007? That 0.007 is not coming from the number of electrons. It's coming from most of the nitrogen in nature is going to be this one right here, 99.6%, but occasionally there's a little bit of this, 0.4%. And when you put this together, you get an average isotope of nitrogen out there. If I averaged them all out, would be 14.07, just a little bit over 14 because there is some of this in nature. What's the term synthetic mean? Ever hear the term synthetic? Is it natural? No, it's going to be man-made. So there is other forms of nitrogen, like nitrogen-13, that can be made for a fraction of a second, and then it disappears. But in nature, you're not going to find that. So when we're looking at this number, we're only looking at an average of the types of nitrogen we find in nature. And so that's going to be N14. You're going to hear the term nucleon. That might be something, have you heard the term nucleon before? It's pretty simple, but if you haven't heard of it, it's just the number of protons, the number of protons and neutrons, the things that are bigger in the atom. So if you see nitrogen 14, it has 14 nucleons, and its atomic mass or atomic weight would have been 14. If you see nitrogen 15, it has 15 nucleons. Since all nitrogen comes in with seven protons, it doesn't matter what. If it's nitrogen, it has to have 7 protons, then everything else that makes up this number of nucleons is coming from those neutrons. So it just becomes a subtraction game. Okay, so this is just getting the atomic mass. Once again, I already mentioned it. The reason why this number is so close to 14 is because you find mostly 14 and 14 in nature. You find a little bit of this, which is really the reason why you have that little extra fraction. And so let's go ahead and let's work together, determine the number of neutrons in the element radon-220. So look at this right here. And this is what you have to do. This is important. When you get to this point and you see radon-220, everybody see that? When you see radon-220, look at this part. Look at what I'm going to do. Don't do this on your paper, but this is pretty much like saying this. Everybody see that? See what I just did there? When I tell you radon-220, you no longer are going to look at the 222. We're looking specifically at one type of isotope of radon that has 220, the atomic mass of 220, atomic weight of 220. So 86 come from protons. What am I going to have to do to that 22 to figure out how many neutrons I have? If it's 220 nucleons, I have to do what? 220. It's going to be plus, minus. What am I going to do with the 86? I'm going to have to subtract it. I'm going to have to take away. So I take the overall nucleons, which would have been 220 for radon-220 specifically. If I asked you for the average radon, you would have used this number. But when I say using radon-220, you would take that 220, you'd subtract the number of protons from it, right there. That's always going to be the proton number. I'm never going to cross this one out. So when I change this, I'm just changing the number of neutrons, because radon, to be radon, has to have 86 protons. I subtract the protons from it, and I get the number of neutrons as a result. And so that's what we're doing here. When we think of nitrogen's 14, we have 14 nucleons. We know 7 of those have to be protons, and therefore that nitrogen, we take that 14 minus the 7, and we get 7 neutrons as a result. So that gets us to the answers. We're pretty much done with our lesson. You're going to have a quick quiz after this. I already put a video online, but it should be a review. But you can kind of catch up right here. If you're just coming into the lesson, I know someone just showed up in the Zoom. Let's go to answer these questions real quick, starting with that first one. You have it in front of you. And then we're going to have a 10-question quiz, and you'll be done for the day. So make sure you focus and try to answer these questions first. Don't jump straight to the quiz, because once you answer these questions, you're more likely to be successful the first time around on the quiz. I did make it so you have to take every single question. Like you have to, if you're going to do the quiz the second time around, you have to do every question again. There's no math. It's basic. There's no reason for it to be any difficult. So how many protons does nitrogen 15 have? What would our answer be here? Nick, I know you know it. What's it going to be? How many protons does nitrogen 15 have? Yeah, 7. Nitrogen will always have 7. It doesn't matter what the number is after it. Next one, how many neutrons would nitrogen 15 have? Going to be 8, exactly. When it says nitrogen 15, you ignore this and you say, I'm looking at specifically that one right there. If watch out for the quiz, when I say the average nitrogen, I will not say nitrogen 15. I would, if I said just nitrogen, the average nitrogen, you would look off of that, you'd round it to the closest number, and you'd go off of that. Number 3, how many neutrons does nitrogen 13 have? So the synthetic version of nitrogen, what would that have? What do you think? Emma, how many? Yeah, it would have 6. Once again, if it says nitrogen, if it gives you a number, we're no longer looking at the average. We know that this number has to be 13 for that one because of this right here. If you just see nitrogen, you're going to go off of this number. But if you see a specific number like that, you're going to go ahead, and this is pretty much what you're doing, is your nitrogen 13 is saying all nitrogen has 7. It's always going to have 7. It can't be nitrogen without having 7 protons. But it's this number, which is going to be, it's going to take over that 14 because we're looking at a specific isotope when you have a number next to it. Okay, so how many protons does uranium-238 have? What would that have? I have it right here in front of you. It's going to have 92. Perfect. And one last question, and then you're pretty much done except for the 10-question quiz, which asks you the same questions. So how many neutrons would it have? Close. Everybody's close. Everybody's trying to get the answer first, but there it is. So 238 minus the 92, you get 146. And so that's all you'd have to do. And in fact, if I just said uranium, it would have been the same number because that averages to 238. But this specifically was saying, okay, this is the uranium I'm talking about. Yes. The what? So if it has this right here, if I didn't tell you this, you would look off the periodic table, you'd say this is the number of protons, and you'd say, okay, this is closest to 238, so this is the number of protons and neutrons, and you would subtract, you take this number, subtract that number from it, and that would equal the number of neutrons alone. But if I told you something like this, uranium-240, then that says, okay, well, this is 240, that's the protons and neutrons, and then you're just going to subtract the number of protons from that, and you would get the number of neutrons. So if I don't tell you anything here, you go off of the closest thing that this averages to. Sometimes it averages to the higher number, sometimes it averages to the lower number.